We've already used it several times today and perhaps taken it for granted, but hopefully everybody will be familiar with Galileo and his experiment with dropping the two balls off the Tower of Pisa, one of a dense material like lead, one of a less dense material like wood, drops them both off. They've both got the same aerodynamics, so that's not a factor, that's a control variable. And they both hit the ground at the same time, even though one is so much heavier than the other. And that's because all objects accelerate. Their acceleration due to gravity is the same, or at least at the surface of the planet. Obviously, if you go off into space, the gravity will be at a different level to what it is on planet Earth. But for the vast majority of human experience, that's exactly where we'll be. So, as the slide says, all objects neglecting air resistance, and do remember that that is a fact. If you drop, for example, if you'd done that same experiment, but they hadn't been the same shape, if you'd had like a flat discus, and the other one was a thin pencil, and you drop them, then they would hit the ground at different times because air resistance would affect them differently. But neglecting air resistance or factoring it out by having the same shape, they fall at a constant rate in a gravitational field regardless of their mass. The descent of cannonballs rolling down ramps is the slightly more grounded experiment he did. This constant rate, by measurements, we've shown it to be 9.81 meters per second squared. If you think that's very specific, that is because it is particular to planet Earth. So don't go applying that if you're given a question where it takes place on the moon or something. Please don't go using 9.81 because it's only true of planet Earth. We can demonstrate the principle of constant acceleration due to gravity by doing a tribute act to Galileo, or if we're in our classrooms, we can resolve a force diagram for an object using Newton's second law. Okie dokie, so force diagram, as always, there's weight. That is equal to mass times little g. But, so the force is the weight. But this also has to equal the mass times the acceleration. So F equals ma applies generally to forces. The so-called inertial mass of an object. And the force in this case, perhaps I should write this equation actually the opposite way around. So it's F equals ma. And then I'm clarifying that in this particular case, we're talking about gravity. And this is what we used to call the gravitational mass. And scientists for a while used to ponder, well, you know, is the inertial mass fundamentally the same as the gravitational mass? And it all gets a little confusing. And we don't generally talk about it at A level. It's not on the syllabus. But for those of you interested, and it turns out, well, hey, these two things are the same, the inertial mass and the gravitational mass, and you can cancel those two. And you can say, look, G literally is just the acceleration from Newton's second law associated with gravity. Nice. Makes things a lot simpler. It would be a bit of a headache if we had to start using two different masses for each object. Hooray. Okay, this is a bit of a nightmare question, isn't it? One sentence, you look at it and you think, yes, that's probably only 1 mark. No, sirree, 4 marks. Plan an experiment to measure the acceleration due to gravity. Oh, terrible. It's an experimental analysis question. Not as bad as it could be. It's only 4 marks rather than 6 marks. But the saving grace is that it is a plan question, so you can at least get at least 1 mark from drawing a nice diagram. As our slide says, make sure it's neat and easy to interpret. We don't want, it doesn't have to be artistic, but just, you know, clean straight lines, nice and labeled. That will stand you in good stead. And we want to detail our measurements. So if you are doing a question to measure the acceleration due to gravity, you might draw something like this. This is quite an advanced example. Clearly, I think in this case, we are looking at an electromagnet, just as a method to drop our ball. You've got yourself a ruler or a rule. The difference between a ruler and a rule, I'm reliably told, is that a ruler has like a little bit of extra plastic at the end, where there isn't, you know, there aren't the gradations, whereas a rule ends at 0. There you go. I didn't learn that until I was, you know, out of uni. So if anybody ever asks you, you can blame me. Right, in this setup, this looks to me at the bottom like a light gate, or it's linked to a timer. So we'll trigger our ball's fall from rest using an electromagnet, and it will fall and break our light gate, and that will set off our timer. Right, one more. 1 mark for just saying drop a small ball, for which we can neglect air resistance from a height, measure the height using a meter rule, and measure time using a stopwatch timer. Sure, you don't have to have an electromagnet. You don't need to be fancy with a light gate. You can just do it with a stopwatch. The mark scheme for these 4 to 6 mark questions, as we saw earlier in the day, they're quite loose. They tend to say things like, any sensible suggestion. So as long as you're not proposing a sort of elaborate Wallace and Gromit style machine to measure the fall of this ball, generally, and there's a clear diagram, then generally you should be okay. Use a stroboscope, which flashes periodically. Okay, this is an alternative method instead of just using your timer. That's a very niche method. I've never seen a student write that before, but yeah, it'd work if you just film the descent of your ball and have a time signature in the bottom of your video. You can also just analyze it that way. Have the ruler in the background, note off at certain times. That'll work. Or have ball fall from electromagnet onto trapdoor, which breaks time switch. That's what we had on the previous slide. Okie dokie. So I think those are supposed to be 4 alternatives. Plot graph of distance against time squared. Why would we choose that? And measure acceleration due to gravity. Well, it's because of Suvat, really. It's if we're plotting distance against time squared, we're thinking of this Suvat equation, half AT squared. U is 0 because we're dropping it from rest. So this should be at play. The acceleration is the thing we're trying to measure. Should be g, but it, you know, our experimental value might be different. So if we plot s against t squared on the y-axis, so y equals something times x, that something should be equal to half g.